Good luck, Penny.
Thank you.
Oh, you're so pretty. Oh, it's blue. Oh, was it pink? Yeah. Okay. I'm doing reverberation time like Coda, so it's going to be a bit repetitive. Reverberation time is the reverb, basically, of in a room, and you can calculate this in seconds. In a live environment such as a church, the reverberation time will be high, whereas in a confined space, it will be like dead environment. History of reverberation times. Wallace Clement Sabine is the most famous for his calculation in the 1890s. However, Greek philosopher Pythagoras was the first to experiment on vibrating strings, and he went on to do the tuning system. Acoustics is an important application in every area of life, and architectural acoustics has been learnt through trial and error. I missed out a bit. Oh, no. The study after Pythagoras was by Galileo. I don't really know what he did though. I think it's general. An example of early acoustics is the Berlin vacuum experiment. This is where it uses a jar pumped with air where a ringing bell is placed. As the air pumps out, the ringing sound decreases until it is inaudible. The other calculation is by Norris Earing, how do you say his name? It was developed in the 1930s and is similar to Sabine's equation, but it's a bit more complicated. T60 is obviously the reverberation time, and N equals log in the equation. In this equation, sound visits all surface areas equally. However, this formula can't be used on circular areas like the Sabine one. Compared to each other, Sabine's equation is said to be easier and gives accurate results as long as the absorption in the calculation is less than around 0.3, whereas Norris Earing's equation assumes that the reverb field is diffuse and that the room being treated is of an average shape. Yeah, it's supposed to be more accurate as well. The RT60 equation that we use locates problem frequencies, and it's based on the volume of the space and the total amount of absorption in the room. Okay, so you do the absorption by using coefficients for each frequency times by the area of the floors, walls, and ceiling separately, and that gives you the absorption. And then the volume's a bit easier. You do multiply the length, width, and height of the room. I've got an example of it. It's a bit messy. So say the floor absorption coefficient was 0.02, times that by the area, which in Studio 2 control room was 13.99, and then it equals this. And then you do that for the walls and ceiling, and add them together, and that gives the absorption. And the volume for the whole room was 40.58, so you divide that by the answer. And then times that answer by 0.161, and you get the reverberation time. You can then put these in a chart like this for each frequency, and then make a graph to show where the problem frequencies are. So they're around the 250 Hz and 500 Hz in this room. And to change this, to treat the room, you can add wood paneling. I've found a 1/4-inch plywood for the coefficients for that, and added that into the equation, and got this chart for the treated room, which flattens out the reverberation time. It doesn't look like it does, but it's like magnified, so it is. The there are problems using RT60 in general when